So first of all, I want to introduce Gianmarco Marmoni, the speaker of today. I'm just doing a short introduction, and then Gianmarco Marmoni, a researcher in engineering geology from Sapienza University, will present some interesting case studies on rockfall detection. If you join the other webinars, you already know me. I am Vera Costantini from NHAZCA, business developer and project manager. I have a background in satellite data management and analysis, and also in business development in this sector. Just a short agenda. I will present NHAZCA in a very few words, and also what is photomonitoring, because we can, if we have people that did not join the other webinars, we will do a short introduction to the technology. And also the first webinar of this series was in March, so also people that already joined the webinar maybe are happy to listen to some of the most important things about photomonitoring. And then why study rockfalls, and the introduction to geoscience projects, and some case studies with the fixed solutions and periodic solutions, and some information about how to ask the photomonitoring service to NHAZCA, and the Q&A section. NHAZCA is a spin-off of Sapienza University, and we collaborate with the university nowadays. You can see from the fact that we collaborate with also with Gianmarco, and we are a leader in providing monitoring solutions with remote sensing technologies for land and infrastructures. And we also invest constantly in research and innovation, and we have a team of all graduated professionals, geologists, engineers, physicists, academics, and so on. But what is photomonitoring? It's a technology that NHAZCA employs in many different projects. It was developed to take advantage of the great availability of optical and also non-optical images acquired from many different platforms, including cameras, drones, but also smartphones, and of course from satellites. And this technology enables the monitoring of changes and displacements. So it's two different types of analysis, and operates at many different and multiple scales, from large territories that can be monitored with satellite images to individual buildings. Just to give an idea of the two different analysis that can be performed. Change detection is about the detection of changes, of course, and also the appearance and disappearance of objects, of targets. When we talk about displacement detection, instead we talk about the detection of any kind of movements, translations, rotations, deformations of the target in the scene. And what are the issues, the problems that we can encounter when we want to analyze multi-temporal images? One of the most important problem probably is the co-registration problem, so images that are not well aligned to each other, but also illumination changes and problems related to weather conditions. But also moving objects in the scene that we're not interested in, and that create noise and problems in detecting the real changes, the real movements. All these issues are, let's say, addressed and can be solved through our algorithms implemented in our software. So with co-registration algorithms, and also radiometric preprocessing for the illumination change, for example, but also statistical and spectral analysis, and also post-processing filters for the, for example, if you want to draw a mask to analyze only some parts of the image. How we solve these problems with our software Iris. just a short video that to show how it works, for example, for change detection of multispectral satellite images like Sentinel-2. And we can see that this user interface that actually is being implemented and improved constantly. And we can see that there is a change detection analysis, and in green we see what has not changed between the ref image that we call master image and the slave image, so the secondary image. And in colors from yellow to purple, the different levels of change. When we talk about displacement, instead we talk about another kind of analysis in the software. Through displacement analysis, we have a very great measurement sensitivity of less than 1 pixel. So we can detect very small movement. Let's say we have a satellite images to analyze with a geometric resolution of 10 meters, for example. We can detect the movement of an object at less than 10 meters. For example, we can reach 1/10 of a pixel, but also better if the conditions allow this analysis. With the displacement analysis, we can have also multi-master analysis, so that we can use, if we have more than 2 images, each image can be used as a master and as a slave in different and consecutive correlation cycles. In this way, we reduce the ambient noise, we increase the accuracy, and also the possibility of long-term analysis. And also we have, in this case, we can generate time series of the displacement, of course. Just some of the, to understand which are the platforms that can be used to acquire data for photomonitoring analysis. As I said, we can use drones data, but also data from a webcam, from aerial data. This is in the center of the slide. We see comparison between 2 DTMs created with the LiDAR data, and also from a smartphone in the lower left part of the slide. Okay, so now I will leave the floor to Gianmarco Marmoni. So I will stop sharing.
Here I am. Can you hear me, Vera?
Yes, perfectly. Okay, please, you can share your screen, and if you want to introduce yourself, of course.
Yeah, but you already introduced me very well. Good morning, everyone. While I'm sharing, let me present myself. I'm Gianmarco Marmoni, a researcher in engineering geology in Sapienza University of Rome, in the Earth Science department. And my expertise mainly focuses on rock instability modeling and monitoring. And in recent years, I focus on the application of digital image analysis and photomonitoring for rockfall studies. Just give me a second to share the screen, because I'm not so happy with Zoom platform. Okay, you should see my screen now, right?
Yes, we see your screen.
Perfect. So thank you again, Vera, for the introduction and the opportunity for being here in this webinar. Today, as you introduced, we will focus on real case studies and applications of photomonitoring to rockfall. And despite most of these concepts are well known to the audience, let me introduce why it's important, and concurrently how difficult it is to study rockfall. You know well that because of their kinematics, they are featured by very high intensity, mainly because of the fast speed they can reach and the large runout distance they can cover. Rockfalls can be caused by meteorological triggers, but more frequently than you could imagine, they can also occur without any major triggers, as effect of mechanical degradations, like the process acting on permafrost, for example, or in any other natural context. These rockfalls are becoming more frequent, as more frequent and intense are the main meteorological drivers and pluviometric events that cause frequently instability. They do not show any deformation, almost any deformation prior to the failure, and clear or detectable precursory signal, especially for the smaller size events that are so far no visible. The high velocity of this process results in almost null response time, and consequently the ability to monitor and adopt some countermeasures or monitor before the failure for mitigations or warning purposes is very limited. The source area of the rockfalls are distributed over large cliffs, like in wide mountain front, or long corridors like road cuts or roads or rails. And this makes the geotechnical, for example, contact monitoring impractical, because it's not possible to instrument many unstable blocks. At the same time, remote sensing can sometimes be either too periodic or very site-specific, or too expensive one should adopt active radar technology or other remote sensing techniques. That's why risk mitigation strategies must focus only on passive strategies and mostly encompass the structural countermeasures, like the use of retaining wall, fences, and bolted mesh, and adopt land use regulation in a passive way through a multi-step procedure that include the susceptibility analysis and the modeling of runout. In this context, the photomonitoring does arise as a new integrative technology for the monitoring of rockfalls activity in a distributed way over large territories, because the photomonitoring is capillary, is cost affordable, and very flexible solution. Capillary because digital image processing can rely on the fast technological improvements of the photographic sensors and the widespread diffusion of the camera. Let's think about the large number of webcams and cameras that are available, for example, in Italy nowadays. It's also cost affordable with respect to laser or radar remote sensing technologies, and it's flexible and adaptable in both coverage and resolution, since allows to frame large areas or give attention and goes a focus on specific sectors. The photomonitoring do not need any physical targets, and that's why it's very, very flexible. Can be periodic, so some surveys per year, namely for a knowledge monitoring of the rockfall process, or continuous for operational purpose or alerting, and can be both ground-based or benefit of aerial or UAV survey. But the question is the photomonitoring to date really applicable as a landslide monitoring technique? So to answer this question in the frame of a national research project founded by the Next Generation EU, named Geosciences, led by ISPRA in Italy, in the research group of Sapienza University of Rome, we aim to evaluate the applicability and the accuracy of this technique, integrating the image analysis into the landslide monitoring sites that are already managed by the regional geological services. As a general objective, the project has a goal to apply the photomonitoring to increase the number of landslides that are currently monitored in Italy, which do not exceed the 0.2% of the total landslides inventoried in our peninsula. And so to pursue this goal, we installed several photomonitoring systems over 15 sites across Italy, testing the digital image processing applicability with different types, styles, and mechanisms of landslides. The instrumented sites in the project span from the north to the south, covering the Alps and the Apennines down to the Sicily, including processes like rockfalls, today's topic, but also air flows or more complex landslide mechanisms. In this frame, we adopt different monitoring solutions and the acquisition strategies, including as I mentioned, the deployment of new cameras, but also the use of UAV to frame digital images and gigapan robotic head, or also the post-processing of images acquired by already existing cameras and that were managed by the regional authorities in charge of the landslide monitoring. Here you have a little showcase of the permanent solutions where we install different cameras from different producers just to test the applicability of different products with different sensors and resolution, spanning from standard webcams to ad hoc multi-optics surveillance camera or reflex systems integrated with Raspberry Pi and some internet access point to make the monitoring accessible by remote. Concerning periodic monitoring solutions, in some site we processed orthophotos generated by photogrammetric reconstructions. For example, on the site of Camogli, in Genoa, we process images acquired by planned UAV flight with nadir and off-nadir acquisition modes. That such activities were completed with the support of the technicians of the Liguria region and the ARPA Piemonte that get the images for us, and we take care of the post-processing of the acquired pictures, just to have a feedback about the applicability of photo monitoring on different images that we not directly collected. In Piemonte and Sicily, for example, we conducted also a gigapan robotic head survey and processed with the change detection algorithm large panoramas that were previously generated by the stitching of single photograms with the specific aim of increasing the geometric resolution of the standard images and increase the aerial coverage of the survey. Specifically for the image processing, we benefit from the IRIS software that was developed by NHAZCA, and the software integrates in the graphic user interface that Vera just introduced before, several algorithms for the image pre-processing, including the filtering or image equalization that is useful for selecting the most appropriate pictures to be used for change detection, while the other algorithms at the core of the automatic or manual change detection, or the one at the base of digital image or face correlation that are devoted for the displacement analysis, and so the monitoring of displacement of targets. Given the Rockfall topic of today, we'll mostly focus on change detection analysis, because Rockfall can be radiometrically seen in an image as an appearance or disappearance of new elements in a scene. As a main photo monitoring product, the change detection analysis provide a false color map reporting the pixel by pixel the value of the structure similarity index, and that express in a range between 0 and 1 the degree of changes between two subsequent frames, the master and the slave. Changes that are function of variations in the luminance, in the contrast, or in the structure of the images. Other complementary products of the digital image processing are the displacement analysis map, which represent the flip side of the coin, with tracking and cross-correlation techniques. We are able to providing time series of displacement in the entire scene or within some specific analysis marks, like the one that I, for example, can show you here in the center of the slide. Now let's skip to some real-world applications, which I divided in the following slides. For one, that adopts customized camera, and namely cameras and sensors that are specifically selected in the market for the context and the site. Afterwards, we will talk about the UAV-based images and gigapan panoramas acquired with the robotic head, or digital image processing conducted on images get by surveillance camera that are owned and previously installed by the regional geological services in charge of the monitoring. First example is from the Gollone landslide in the Western Alps at the border with France, where we monitored the main scarp of a former rock slide, where recurrent rockfalls occurred and where a single rock pillar is isolated, as you can see from the picture now, by a vertical trench, and this block is prone to detach. And for this reason, this block is on the focus of the regional geological service that installed a network of wire extensometer. Given the large distance of the target from the camera, which was somehow constrained, somehow obliged by the logistic reasons, we selected an Ultra HD camera with two distinct optical and different field of view, getting pictures every 30 minutes in the daytime. The two optics had different focal lengths and respectively a field of view of 30 degrees and 8 degrees, which guaranteed a resolution per pixel, so the one that we call ground sample distance, of 50.6 and 3.7 centimeter per pixel, depending on the focal length. The panchromatic telephoto lens, for example, the second lenses we adopted, allows for the detection of changes in the images from very large distances. That was about 1,000 meters. And as in this example, identify a rockfall event. This event, the detachment is not visible from these views with clear and human eyes. But if we overlap and co-register the two images, apart from the changes in the luminance in the bare outcrop, we can appreciate a difference in the structure of the images. Here, just below the trees, you can see an object that appear and disappear. Change detection makes this process clearly visible, showing the minimum value of the structure similarity index in the scar area and highlighting also the accumulation zone on the basal debris fan. This detachment involved an area of approximately 1,000 pixels and thus an area of, given the ground sample distance, of about 1.65 square meter. And consequently, if we assume 1 meter in the third dimension, similar numbers in volume. Remember that these rockfalls were detected with an optical camera by a distance that was more than 1,000 meters, so something really relevant. This rockfall is one of the biggest in the area during the 2-year monitoring, but with sequential change detection, we were able to recognize about 50 small rockfalls and as many changes in the debris caused by the movement of single blocks just below the main cliff. It's worth noting that several rockfalls occurred apparently at the border of the rock pillar that was instrumented by the regional authorities with the wire extensometer, and which since April 2024 has shown a stark acceleration in the rate. We are still working on it by cross-correlating the rockfall activity with the displacement and also with the available microseismicity, because over there in a different project we also installed with the colleague of the University of Torino a triaxial accelerometer on top of this block. But example yet prove the large potential of the image analysis. Since we are in the Alps, snowfalls frequently cause blanking of large areas and many false positive in the analysis, not only rockfalls unlikely. This makes the stressed the importance of the image filtering, the image segmentation, and the post-validation crucial for the analysis. In addition to snowfall, you can also see that in the project we experiment some new algorithm that we can call deer detection, while in some sites birds or cows frequently used to walk into or fly into our scenes. But getting back to Sirius, in the study of rockfalls, I cannot avoid citing the experience that we gained in the Poggiobaldi landslides, a field laboratory financed, developed, and managed by the Sapienza and the Cherry Research Center for Geological Risk, which is part of the network of the field laboratories for landslides, included in the ICL War Center of Excellence. You probably could have heard about Poggiobaldi in recent time because it was in the technical visit of the very last international course on geotechnical and structural monitoring that was organized by NHAZCA in Poppi. The sites includes a large set of active and passive sensors for remote monitoring of rockfalls event and slope failure in general, because the site show a very high activity and an ordinary production of more than 3,000–4,000 cubic meters per year. Today we will focus on the photomonitoring, not in the other technologies. So I just want to give you an overview of what we have done there with different cameras. Over the last year, the rockfall production rates were constantly framed by panchromatic camera with a resolution of standard resolution of 5 megapixels that was able, given the distance, to guarantee a ground sample distance of 70 centimeters per pixel. With this camera, we deployed an automatic day-by-day change detection analysis, which consists of cataloging and filtering the daily pictures acquired on the site, adopting for the following change detection analysis only that frames that are similar with our standard reference images, thus avoiding and filtering those images with clouds, rain, or fog, or overexposed images can be less relevant for the or noisy for the change detection analysis. The daily automatic detection allows, after validation, to populate an inventory of rockfall with more than 100 events, variously deployed and located over the scarp. And thanks to available laser scanning acquisition, we get an estimate of the ground sample distance and convert those hotspots of pixel, because you know that change detection initially give us information about pixels, into metric dimensions to do further analysis. Given the acquisition rate, we obtain a very detailed multitemporal inventory with also sizes of the rockfall events in terms of areal dimensions and all the informations that are essential for understanding the distribution and the frequency of the event with respect to their intensity, their magnitude, and namely to infer the rockfall hazard on a cliff. In the paper of Mastrantoni and others in 2024, we went in this direction by calculating the frequency of the events in a 10 per 10 meter regular mesh, regular fishnet, sorry, generated onto an orthomosaic of the cliff and adopted to standardize and make sorry, comparison in the calculations.
Gianmarco, if you need to take a break for drinking, please feel free to do that.
Sorry, I was a little bit fluid. So I will try. Given the lack of the third dimension, the frequency magnitude relationship have been expressed in an inverse cumulative terms with respect to the rockfall area instead of the volume. And afterwards, if we assume the uniform and constant conditions, the frequency of the rockfalls will increase proportionally to the period and the extension of the source areas. Therefore, the frequency need to be normalized per unit of time and divided by an area. This operation allows to compare the activity of different portions of the slope and the involved lithologies. On this data, assuming the process as a steady state process in time, the probability of rockfall, PF, of having more than one rockfall during a reference period of duration T on a slope with a failure frequency that is equal to lambda, we can calculate the probability using using a Poisson law. Now, since the magnitude frequency for rockfalls can be modeled as many other natural processes by a mathematical power law, we fitted the empirical distribution with a power law relating the failure frequency estimates for different magnitudes expressed in terms of area, as I mentioned. Inferring in this way a spatial and temporal probability of rockfall for every pixel of the fishnet. The law assumes this mathematical form, AST, multiplied per A to the minus B, where A and B are respectively describe the normalized or unitary activity, which represents the number of rockfalls of magnitude greater than 1 square meter detached from the single cell of the cliff in 1 year, while B is the uniformity coefficient that expresses the slope angle of the distribution. But apart from failure hazard analysis, the high resolution inventory given by the permanent photomonitoring allow to infer the daily rate of rockfall production, extracting the time series of the number of rockfalls and allowing to make correlations with the main triggers, like the intense rainfall, for example, that occurred, for example, in May 2023 or in the last March 2025. Events that reach value intensity, daily intensity close to 100 millimeter per day, causing more than 30 rockfalls in the cliff with volume ranging from some cubic centimeter to several cubic meter. With a different camera, with higher resolution, further clusters were identified in the following years, confirming the continuous production of the cliff, but improving the geometric resolution and the capacity of detecting smaller events. But this resolution was not enough to go deeper in the rockfall mechanisms and looking for a better understanding of the events that anticipate the major instability, so the rockfall precursory events. To do so, we took the advantages of the Mobotics S74 multi-optics systems, which we selected with two 8-degree lenses featured by a resolution of 8 megapixels, which allows to frame the most active sectors of the cliff and increase the ground sample distance of 1 order of magnitude with respect to the former camera, reaching about 2 centimeters per pixel in resolution. The very narrow optics and the high resolution allows to identify in detail small rockfalls in the arenaceous strata of the flysch formation that outcrops in the area that was not achievable with the standard camera mentioned before. Here an example of master and slave images and the results of change detection. In particular, this high resolution camera get insights on the stability process before and after a failure. And what we saw in several cases is the location of minor raveling in the weathered marls or the detachment of small blocks at the borders of the area that we'll experience in the following week look to the date, have a look to the date, a bigger rockfall event. So somehow this small instability represents a sort of precursor of the major one. The time scan of the rockfall is so high and detailed to reveal also the rockfall propagation, the polarity of the instability in this rock mass. With an upward migrating sequence of the instability, you can see how the hotspot of change detection migrates upward. In this example, you can see the progressive response of the system and the failure of cantilever blocks. For example, after the removal of the basal support, which in turn can look at the relationship between these two clusters. The removal of basal support, which can be in turn located into the marls or in the arenaceous strata. But small rockfalls can also anticipate larger rock slides, as testified in the last March, when after an intense rainfall and mobilization of the debris talus below, the right shoulder, I invite you to have a look here, experienced a 35,000 cubic meter failure after some hours of impulsive displacement. If you focus on the left here, you can easily see some displacement in the blocks and also movement in the trees on top. Before the major rock slide, several rockfalls and debris movement were identified by change detection, as much as a larger structure similarity index anomaly results after the main event. But more importantly, on more than 140 images that were triggered in a few hours by motion tracking algorithm, we were able to follow up and highlights with digital image correlation a fast accelerating trend, a sort of creep-like, tertiary creep-like mechanism before the ultimate failure. Almost perfect time series were extracted by the image analysis, but this is another part of the story, and I will focus more on change detection. Now, very fast, I will show you some results about the periodic UAV acquisitions that are functional to the rockfall photomonitoring over larger areas. I give you the example of the Castellaro Cliff close to Camogli in Genoa, where with the support of Regione Liguria since 2023, we have performed 5 UAV flights and as much photogrammetric reconstructions, covering more than 1,500 meters of coastal cliff, 160 meter high, generating 3D models and orthomosaics consequently, with a ground sample distance of 3 centimeters per pixel. The change detection there allows the identification of 29 significant rockfalls and debris movement between November 2023 and March 2025, with various size, ranging from minor falls of some tens of centimeters inside to massive debris movement reaching up about 2,000 square meters. Here, some example of before and after images and the resulting rockfalls that contributed to the generation of high resolution inventory on a so long cliff. Regarding surveillance camera, so just to wrap up, the camera that were property of the regional authorities that were already installed in the landslide sites before the project, that we do not selected site by site. I show you the results from the Ruinon slides, where the webcam installed there by ARPA Lombardia gave us a sort of legacy of some months of past images in the frame of the Geoscience IR Project 2. On these pictures, we identified some rockfall event and debris slides, However, given the very large distance and the poor resolution of the webcam, we had limited performance in detecting small rockfalls. Conversely, very good performance was instead achieved in the monitoring of the main sliding of the Ruinon landslide, mainly because of a better trade-off between cumulative displacement from the landslides and the resolution of the camera. But this is again out of today's topic and will be probably part of next talks or next webinars on photo monitoring by NHAZCA. So I invite you to keep in touch. At the end, to improve the issues related to the geometric resolution and improve the limit of detection of rockfall, we had with large panoramas and large scenes and large distance, we experimented the use of reflex cameras with the robotic head that assist us in the definition of high-resolution panoramic reconstructions. In 3 different sites, by stitching high-resolution images, we get a full-resolution images of with a Canon standard photographic reflex camera by Canon that was featured by a resolution of 24 megapixels, from which we derived 5 gigabytes of panoramic images with a ground sample distance of 4 millimeter per pixel, like the one detected in Poggiobaldi or here in the Monte Rosa in Piemonte region. In the small video, you have an example of the very high details visible with large panoramas and the detail we can reach, for example, in Poggiobaldi, where we were able to detect very tiny rockfall or reveling. In general, the periodic surveys with Gigaban shed lights on the pros and cons of the adoption of this platform, like the possibility of framing very large areas, up to 100 of meter, I would say, with high resolution, and the affordability of the photographic survey, which is really fast and cheap. As a cons, and this is an example, the Giga panoramas have very large and hard to manage image size that, however, can be used and processed in the Iris software, and also the large processing time that these images requires. The stitching of large panoramas with different depth of field and large view angle can also introduce some geometric distortion or perspective correction here at the borders that have to be taken into account, as much as temporary and periodic acquisitions should also take into account variations in the luminance or contrast among different surveys over different seasons or different years. So this type of survey has great potential, but also you should design the best solution to your specific case studies. Before concluding, and sorry again for my voice, let me acknowledge the whole group that did most of the analysis I show you today, including Antonio Cosentino, Antonio Molinari, Carlo Alberto Stefanini, Gian Domenico Mastrantoni, Giacomo Santicchia, and Rea Rossetti, who are now part of them in the NHAZCA team. Thank you again, and I give you back the floor to Vera.
Thank you very much, Marco. This was very, very interesting. And I will share my screen again just for some final
Meanwhile,
information.
I drink a glass of water.
Yes, go, please, go. Okay, just a second. Okay, first of all, I want to thank you for the attention and also for the questions you wrote in the chat. And I want also to recall that this webinar is recorded, so you will, and in the next few days, you will receive an email with details to see the recording if you didn't follow all the webinar, for example, if you want to share with your colleagues and so on. How to request our services for rockfall detection, but also for any other application of photo monitoring. Of course, identify your needs and contact us, and we define the solution together, and you will receive your proposal. The main questions that we might ask are: what is the size of the area, and which is the frequency of results that you need for your monitoring needs, but also what kind of phenomenon do you need to monitor? So are you monitoring a scarp, a building, an infrastructure? So this, of course, can have different kind of tools to use. For example, different platforms, because we can use your data acquired by drones, for example, if you already have some images, or if you need to monitoring with fixed cameras, as you saw for all the examples proposed by Gianmarco. This is another kind. This is a kind of different from drones, because in that case the service is sold in another way.